These are notes for section 10.1, comparing two proportions. Please read the section either before or after you go through these notes with me so that the information sinks in just a little bit more for you. We have our learning targets. There's some vocabulary here. Sampling distribution of p hat 1 minus p hat 2. Basically, we're going to be looking at the differences in two proportions. For the sampling distribution, that's the graph that, let's say p hat 1 is the sample of 100 girls, and we ask them, do they like the color blue, yes or no? And p hat 2 is 100 boys, and we ask them, do you like the color blue, yes or no? And then we subtracted, maybe out of 100 girls there were 40 who liked blue, and out of 100 boys there were 60 that liked blue. So if we do 40 out of 100 and 60 out of 100, the difference would be 0.20. We could look at that as negative or positive depending on how you subtract it. But if you imagine a graph of all the differences of two proportions, the shape would end up being approximately normal, as long as your conditions are met. And the conditions we'll go through in a few minutes. The center, we're going to center it around the true population parameter difference. And later when we do our test for the HO, we're going to state that the proportion of the first group will equal the proportion of the second. Meaning if you were to find their difference, you should always get 0. And then the spread, depending on if you're talking about a test or a confidence interval, it's either going to be your standard deviation or the standard error. So now going to the standard error formula down here. That's used for your confidence interval. And it's the square root of your first proportion, sample proportion, times 1 minus that sample proportion, divided by that first sample size, plus the second sample proportion times 1 minus the second, divided by that sample size. And that would give you your standard error. The two samples the interval for a difference between two proportions, that's really wordy. In your calculator it's called a 2 prop for proportion z interval. The actual formula has always been your statistic plus or minus the critical value, which is z star, times your standard error. The statistic in our case now is going to be the difference of those two sample proportions, plus or minus your z star. The standard error wrote above, square root p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. Now that's for an interval when you don't know the population value and you're starting with just the sample. When you do know your parameter, so we'll say the parameter is given over here, then there's something called pooling your sample proportion, because we assume when we pool or combine the proportions, we're assuming that the two proportions come from the same population. So in order to combine them, it's p hat, and then sometimes abbreviated with the subscript c, sometimes they actually write out pool as the subscript, but it's all your x's or successes from the first group, plus all the successes from the second, divided by the total sample sizes. That is what we use to get our standard deviation that we use in a test. So the standard deviation is the square root of your p hat combined times 1 minus that p hat combined divided by n1 plus p hat combined times 1 minus p hat combined divided by n2. In your formula packet, it's also written as p hat combined times 1 minus p hat combined times 1 over n1 plus 1 over n2. And then that entire thing is square rooted. Lots going on there. And by the way, I forgot to mention this in class on A Day if you're listening. But if we were to actually plug in numbers, that p hat combined will pop up on your calculator. If we hit stat, test, go to a 2-prop z interval, which is number B or letter B. I have numbers in here. I'm just going to stick with the one I used earlier about the boys and the girls liking the color blue. Say it's a 95, calculate, and it gives me p hat 1, p hat 2, and here's my interval. I actually wanted to do a test. If I do a 2-prop z test, keep that same info in there, we'll just say, we'll go with not equal to. Calculate. You're given your z-score, your p-value, p hat 1, p hat 2. If you arrow down, that's your p hat, 0.5. You're given n1, n2, and then I thought it gave you p hat combined, but I guess not. 0.5. Actually, yeah, that p hat right there is your p hat combined. The 40 plus 60 over 100. That's what this one is right here. So p hat combined is written as just p hat given in calculator when you actually run the test. The formula is your z equals your statistic p hat 1 minus p hat 2 minus the parameter. But if we think that the parameter, the two proportions are equal to each other, then the parameter is just 0 divided by this whole mess down here, the square root of your p hat combined times 1 minus p hat combined times 1 over n1 plus 1 over n2. For the randomization distribution, we're just going to ignore that. It's just basically wanting you to go through conditions. And for now, this talks about the concept 1 about the sampling distribution. If you were just to have a whole bunch of differences of two samples, proportions, and graph it and finding a z-score, I'm just afraid that going through too much of this would really confuse you for the more important part of a confidence interval in a test. So here's your state plan do conclude for the test. And we're going to flip to the template really quick to see what the differences are here. For the 2 proportion Z interval, you are, for the state, you're just going to restate what you're trying to find in the context of the problem. And we should also mention the confidence level that you're using. Your conditions are actually the same, except that both samples are random. You're told that both samples are randomly selected. Or we assume that the sample size, the combined sample size, is less than 10% of the entire population. Then we have to check, here it says 5. In the book, they like to stick with 10. So we're going to check to make sure we have at least 10 successes and 10 failures in each sample. Some books say 5, some books say 10. Just know that in your back of your mind that 5 is really accepted as being okay. Make sure that you put words in context of the problem with your successes and failures, like at least 10 girls like the color blue and at least 10 that don't, and at least 10 boys like the color blue and 10 that don't. And notice, since this is p hat 1 and p hat 2 times your sample sizes, for the boy and girl problem, you're really just using the sample values you were given, which was 40 and 60 for not liking blue for the girls, and 60 and 40 for liking blue and not liking blue for the boys. For the interval, here's the crazy formula. Don't forget that you need to put your z-star in there. And the standard deviation of your statistic is listed. And you're just going to go to 2 prop z int in the calculator. It's going to ask for x1 and x2 and n1 and n2. And you're going to put those in from the problem. Remember, if they just give you a percentage and not your actual number of successes, multiply that decimal, the proportion, by your sample size and round. Interpretation of the confidence interval is down here, very similar to what it was before. It says we are blank % confident that the true difference, here's the key change, is that we're talking about the difference in their proportions. Same thing with the interpretation, that the true difference in the proportions will fall between and this is of girls that like blue and boys that like blue, because you have 2 different samples. So let's go back to the actual problem. We've got a 1990, 551 of 1500. So 1990 is my first group. I can abbreviate this as p hat with a 90 next to it equals 551 out of 1500. And they were randomly sampled adults, indicated they smoked. In 2010, so p hat, and I could say this is 2010, maybe I'll change this one over here to 1990. That crazy whiteout. That's 652 out of 2000. And again, they were randomly sampled. Use this information to construct and interpret a 95% confidence interval for the difference in the proportion of adults who smoke in 1990 and 2010. I'm going to leave that as my state and just move on. The plan is that we have 2 random samples of adults with at least 10 who smoke in 1990. I'll put in parentheses the actual amount, 551, and 10 that don't. And at least 10 who smoke in 2010, 652, and 10 that don't. Technically, I should write now with conditions met. I can use the normal model. I'm just going to put okay to use normal model, and then draw an arrow and do 2 prop z interval. So then the do part, because I want what was it, 95%, put 95% confidence interval, so z star is 1.96, and I just need my interval. I'm going to go to stat test 2 prop z int, and add 551 out of 1500, 652 out of 2000, and calculate. And I'm just going to write all that information down. I already have my p-hat 90 up here, 551 out of 1500. So I'm going to just put that equals 0.367, and p-hat 2 was the 2010, so that equals 0.326. That way I'm not rewriting it. And then the interval is 0.0094 to 0.073. Since we're finding differences, if we had done a null or test for this, test of significance, our null would have been that HO was P 1990 equals the proportion of 2010. So the question is, if they're equaling each other, is 0 in the interval? So is 0 in the confidence interval? And the answer to that is no. That implies that you would have rejected HO if we were to actually do a test for this, that your p-value would have been lower than 0.05, or actually 0.025 for 95%, and it's one-sided. Or if it was two-sided, then it'd be 5%. So, don't need to write that though for this interval. I was just connecting. Conclude. We are 95% confident the true difference of adult smokers the true difference in the proportions of adult smokers in 1990 and 2010 falls between what was it, 0.094 and 0.073. Since it's totally above 0, that means that one group is possibly greater than the other. And if you look at the values and how we subtracted, p hat 1 was 1990, then there were slightly more smokers in 1990 than 2010, and about 0.9 to 7% more smokers in 1990 than 2010 is what really that means in context. However, we don't need to write it that way for the AP exam. All right, time out for 1 second. Arthur, are you doing Math Excel?
I'm finishing up the AP stats.
That's fine. When you do Math Excel, make sure that number 1 you just kind of ignore and move on, because I'm going to give everybody a bonus point for it. Okay?
But if you do it, you'll get an extra point.
Yeah, it's just long and ridiculous.
Oh, if it's long, then yeah, I'm not doing it.
Okay.
I'm too lazy.
Yeah.
We just learned about type 1 and type 2 errors last class, and I didn't study them.
We learned them actually the class before last.
Well, like, yeah.
So are you saying you're done for now?
No, I'm just saying that I'm kind of screwed with those problems.
You could be done for now and finish tomorrow. Okay, back to this. Sorry for the delay there, folks. Concept number 3, talking about the tests. P1 minus P2. And here's our state plan do conclude, written out on your reading guide. Notice the HO is always equals. The HA would either be greater than, less than, or not equal to. And remember how it would be shaded on your curve for each of those. If you don't know, this one's pointing that direction, so it would be shaded on the upper end. This one's pointing that direction, so it would be shaded on the lower end. And this one's not equal to, so we would shade on both ends. And then it goes through the plan, and notice we're still looking for 10 successes and 10 failures. They're all the same as the interval. The only thing that's different is this standard deviation down here. And if we flip, and it even shows you how to get the p-hat combined. If we flip to the template, notice that this says standard deviation of statistic. We normally call this standard error. I know on the formula sheet and stuff they call it standard deviation when they mean standard error. That's what we're talking about. And here's all our other information and the fill in the blank for the conclusions. So everything's there for you. Let's go through this problem. School official suspects the difference in the proportion of students who own technological devices between Lakeville North and Lakeville South high schools may be a result of the difference in the socioeconomic status of the students in the two schools. The results of a random sampling of wow, yeah, random, check, that makes you happy. Records indicate 28 out of 120 students at Lakeville North. So give yourself a p-hat for North equals 28 out of 120. And then eventually the calculator will tell us what that equals. And then we also have 30 out of 150 from Lakeville South. So let's call that p-hat S equals 30 out of 150. Now we need to finish reading the problem, of course. Do these data provide convincing evidence? Whenever they want convincing evidence, that should tell you, ding, 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 I need to do a test. I need to do my HO and HA and conduct a test. And they want to know that the proportion of low-income students at Lakeville North is higher, keyword, if north is higher than the south. Well, yeah, north is above south, so yes, it's higher. Use 5% significance level. That's your alpha. So for the state, I've got my HO. Everything's equal in HO world, HOland, whatever you want to call it, that the proportion of the north equals the proportion of the south. And then for the HA, we're trying to see if one's greater than the other, less than, or not equal to. So that's what we just read in the problem, that it's a higher than. So that the proportion of the north is greater than the proportion of the south. Then I need my plan. And again, we have 2 random samples of students from Lakeville North and Lakeville South. High schools. And we also know that at least 10 from each school what were they doing again? Oh, came from low income families. Come from low income. And I'm going to write north was 28 and south was 30 and 10 don't come from low income. So it's okay to use normal model. Do 2 proportion z-test. I'm going to jump to the calculator. And put in my info, hit stat, go to test, 2 prob z-test is number 6. I have 28 out of 120. Second group I have 30 out of 150. And I'm thinking the north is greater than the south. So remember, if you get stuck on this part on your calculator, look back to how you wrote the HA and use that exact symbol. Pick that one in your calculator. And then calculate. So I'm going to write down all that good stuff. I have p hat 1 was the north, so that's my 0.233. P hat 2 was the south, so that's the 0.2. And then I have a p hat combined was the 0.215. My z-score is 0.663. P-value is 0.254. So since our p-value is so high, we would fail to reject the HO. So conclude, since p-value is higher than alpha equal to 0.05, we fail to reject HO. We don't have evidence that the proportion of low-income students at Lakeville North is greater than the proportion at Lakeville South. Okay, so that's the actual test with an example problem. I'm going to flip it over. Again, here's your template. And then we have an actual practice problem. That is a test. It was from 2012. Question 4. I also handed out the rubric in class. If you're B-Day, I'll give you this rubric tomorrow morning and invite you back to class 4th period. Or you can watch this video right now and you don't need to. Survey organization conducted telephone interviews in December 2008, which 1,009 randomly selected adults in the United States responded to the following question. At the present time, do you think television commercials are an effective way to promote a new product? Of the 1,009 adults surveyed, 676 responded yes. So this was in 2008. So P hat 2008 looks like 676 out of 1,009. Now, as I'm reading this problem, I see right away as I glance at it 2 sets of numbers. I see 1,009, 676 said yes out of that amount. And then I see 622 of another sample size. So in my head, we're doing so many out of so many. That's a proportion. And we have 2 groups, so it's a 2 proportion. I see my 2 groups as 2007 and 2008. I haven't even read the problem. Shame on me. So I'm going to know the calculator is going to give me that number later. In December 2007, 622 of 1,020 randomly selected adults in the United States had responded yes to the same question. Do the data provide convincing evidence, ding, 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 you need to do a test, that the proportion of adults in the United States who would respond yes to the question changed from December 2007 to December 2008? Rewind for a second. Who responded yes to the question? Changed. That means not equal to for your ha. So I have 2008. Here's my grouping. And I have P hat 2007 was 622 out of 1,020. So I need to do my state part, which is my HO and HA. So I have HO is that P 2008 equals P 2007. And then the HA is have they changed? So the P 2008 doesn't equal the P 2007. Now technically I should probably write these out in words, but based on the last reading last year grading the AP exams, more students lost points when they wrote too many words up there, so I'm going to tell you not to this year. The plan is that we have 2 samples. Randomly chosen. Of adults from 2008 and 2007. And then at least 10 in each sample said yes. And then I'll write in parentheses 2008 had 676 replied yes, and 2007 had 622 reply yes. And at least 10, they never said they responded no. So we'll just say at least 10 didn't say yes. In each sample. So in 2008, there was 333. In 2007, it's 398. So with the conditions met, I'm going to say okay to use normal model. And do 2-prop z-test. So the do part, and in my calculator, put that stuff in again. Prop z-test. I've got 676 out of 1009, 622 out of 1020, and I'm looking for not equal to. Calculate. Here's my values. I'm going to record them all. Look at that p-value, really low. So I've got z equals 2.823, p-value equals 0.005. p-hat1, remember I wrote them up here before, so I'm just going to put the values up here. 0.6, you don't have to put them up here though. If rounding to 2 sometimes is okay if it doesn't make sense not to. And 0.61. And then p-hat combined, that's that last p-hat on your calculator. It's 0.63097. I'll just go up to 4. And then I have everything I need right here. We haven't drawn in a while. Let's go back and draw. Stat, test, 2-prop z-test. Notice I didn't do it in the last problem. It's good to draw. This one, of course, is not going to show me any shading because the p-value is so low, and oops, something's in y equals. So you can see that it's a little darker on that tail end, but not really, because the p-value is too small to even see. So you probably could have figured that out without drawing. And yes, you should put a picture. I don't always remember to. It's not going to really hurt me on the AP exam if I don't. It's just, if you mess something up and they see that you took the time to draw the picture and it's correct, or maybe if there's a discrepancy and you wrote this p-value down wrong and put 0.05, but over here you had it right, they'd let this wrong one slide. So it's like a backup for yourself. This z is 2.823. It's really all you need to write on your curve. And then the conclude with a p-value lower than alpha equal to 0.05, we reject HO. We have evidence, and I'm going to write the HA in context, and remember the best thing to do most of the time is go back to the actual problem. We have evidence of what? They wanted to know, do the data provide convincing evidence that the proportion of adults in the United States who respond yes to the question changed from December 2007 to 2008. I'm going to rewrite that exact thing to make sure I'm in the right tense and everything else so nobody gets upset with me when they're grading my paper. So we have evidence that the proportion of adults in the United States who would respond yes to the question changed from December 2007 to December 2008. That should be good. If I have extra time and I feel really good about how to write the p-value in context, I would go ahead and do that. If I'm not sure about writing the p-value in context, I might hold off, because if I say it wrong, I could possibly hurt myself for this score, and that conclusion was awesome right there. So I don't want to hurt myself, but yet sometimes it's unclear as whether or not they actually want the interpretation there as well. So let's look at the rubric really quick. And they said because this p-value is smaller than any common significance level, we reject HO and conclude that the data provide convincing evidence that the proportion of all adults in the United States who would answer yes changed. So now we don't need to interpret p-value. Not needed. Yay. So we would have gotten a 4. Pat yourself on the back. Good job.